enthalpies and hydration enthalpies can be used to predict the likelihood of an ionic compound dissolving in water. Before we can make that prediction, however, we need to be aware of the factors that affect the lattice enthalpy and the hydration enthalpies of the relevant ions. Now, lattice enthalpy is all to do with the strength of ionic bonding, and it will depend on the strength of the ionic bonds in the ionic compound. So the stronger the ionic bond, the stronger the attractions, the more exothermic the lattice enthalpy will be. Now, there are two factors that affect the strength of an ionic bond. The first factor being ionic size. Now, the smaller the ions, the stronger the ionic bond. And as we go across a period, we should know that ionic radii actually decreases. This is for ions that have the same type of charge. So positive ions across a period, the ionic radii will decrease, and negative ions across a period, the ionic radii will decrease. We can't compare them both because positive ions will obviously lose electrons, so they will have one less shell than negative ions because negative ions gain electrons. So we can compare the positive ions with each other and we can compare the negative ions with each other. Now, this is because, so the ionic radii will decrease because there are more protons in the nucleus that's attracting the same number of electrons. So here we've got period 3 going from sodium through to argon. Obviously, I've missed out the transition elements because they're irrelevant to period 3, or they don't have any in period 3. So the ions for sodium, magnesium and aluminium will all be positive. So we will have sodium 1 plus, Mg2 plus, Al3 plus, and if you do the maths, they will all have 10 electrons once they become an ion. So they all have the same number of electrons. However, aluminium has more protons than sodium and magnesium. So aluminium actually attracts, or the protons in aluminium will attract the electrons more strongly because there are more protons bringing those electrons closer to the nucleus. Hence why the ionic radii will decrease. So from sodium to aluminium, the ionic radii will decrease. Now we will address the negative ions. So phosphorus will form a 3 minus, sulfur 2 minus, chloride 1 minus. Now again, as we go across, the ionic radii is going to decrease, and it's for the same reason. Now these electrons will all have will all have 18 electrons once they form their ions, but chlorine will have 1 more proton than sulfur, which will have 1 more proton than phosphorus. So again, chlorine, or the chloride ion, now has more protons compared to the other two. So because there are more protons in the nucleus, the attraction between the protons in the nucleus and the outer shell electrons is much stronger, so the electrons are pulled closer towards the nucleus, hence why chloride ion will have a smaller ionic radii than sulfur and phosphorus. And then as we go down the group, obviously ionic radii is going to increase because going down a group, you're adding a shell each time. So if I just stick with group 1, lithium ion will have 2 electrons, and a sodium ion will have 10 electrons. So you can see as you go down the group, you're adding an electron shell each time, meaning that the ionic radii is obviously going to increase down the group. So the second factor that affects the strength of an ionic bond is the ionic charge, and the bigger the ionic charge, the stronger the ionic bonding. Let's stick with period 3 ions as examples. So we've got sodium 1 plus, magnesium 2 plus, aluminium 3 plus, phosphorus 3 minus, sulfur 2 minus, and chloride 1 minus. So again, we can't compare the positives with the negatives. We can compare within the positive ions and within the negative ions. So looking at the positive ions, as we go across the period, we can see that the charge actually gets bigger. So aluminium has the biggest charge with 3 plus, followed by magnesium with 2 plus, followed by sodium with 1 plus. So as we go across a period, we can see that there's an increase in charge. With the negative ions, it's actually the opposite. So we actually have a decrease in charge as we go across the period, because phosphorus 3 minus is bigger than sulfur 2 minus, which is bigger than chloride 1 minus. Putting this all together then, so putting the two factors together, we've got ionic charge and ionic radii. Let's have a look at comparing some example ionic compounds, and the two I'm going to start with are sodium chloride and potassium chloride. So the first thing I want to do is identify what ions are present within this compound. In sodium chloride, we've got Na1+, Cl1-, and in potassium chloride, potassium 1+, and Cl1-. I know that because of the groups that they're in. Now, the chloride ions are the same for both compounds, so nothing changes with the negative ion. So I'm not going to be comparing the negative ions in this case. It's not going to have anything to do with the strength of the ionic bonding, but the positive ions are different. Now, I can't comment on the size of the charge because they both have a 1+ charge. However, the size of the ions is going to be different because potassium is in period 4 of the periodic table and sodium is in period 3. That means that potassium's ion is going to have one more electron shell compared to sodium. So potassium's ion is going to have a larger ionic radius compared to the sodium ion. That means that in potassium chloride, the ionic bonding is going to be weaker because it has a bigger ionic radius. So the attraction between the potassium ion and the chloride ion is actually weaker compared to the attraction between the sodium ion and the chloride ion. And if we remember, the stronger the ionic bond, the more exothermic the lattice enthalpy will be. So in this case, sodium chloride, because it has the stronger ionic attractions, the sodium chloride will have the more exothermic lattice enthalpy out of the two compounds. Now let's compare the lattice enthalpies for sodium chloride and magnesium chloride. Again, the first thing I need to do is identify what ions are present in each compound. So for sodium chloride, we've got sodium 1+, chloride 1-. And this time magnesium chloride, we've got magnesium 2+, because it's in group 2, and chloride 1-. So again, the negative ions are the same, so they're not going to have an overall effect on the strength of the ionic bonding. However, the positive ions are different. And we can clearly see that the sizes of the charges are different. So magnesium has a bigger charge compared to the sodium. So we've got a bigger charge, which ultimately results in stronger ionic bonds. But we can also look at the size in this case as well. So we know that going across a period, they're both in the same period, that the ionic radii decreases. So magnesium 2+ will also have a smaller ionic radius compared to the sodium 1+, which again results in stronger ionic bonds. So we can come to the conclusion, or we can predict, that magnesium chloride this time will have the more exothermic lattice enthalpy because of two things. First, it has a bigger positive charge compared to the sodium, so it's going to have a stronger attraction to the chloride ions because it has a bigger charge. And secondly, it also has a slightly smaller ionic radius compared to the sodium ion. So again, that will result in stronger attractions between the magnesium and the chloride ions. So the second enthalpy change that we need to look at in order to predict whether an ionic compound is soluble or not is the hydration enthalpies. And hydration enthalpies, then, it depends on the strength of the attraction between the ions and the water molecules. So the theory, the scientific theory behind this is exactly the same as it is for lattice enthalpy, but lattice enthalpy, we're looking at the attraction between the positive and the negative ions. With hydration enthalpies, we're looking at the attraction between the ions and the water molecules, because remember, definition of hydration is we're taking the ions in the gas state and we're dissolving them in water to make aqueous ions. And the stronger the attraction between the ions and the water, the more exothermic the hydration enthalpy will be. And it's the same two factors that affect the strength of ionic bonding that affect the strength of the attraction between the ions and the water molecules. So we've got ionic size. The smaller the ion, the stronger the attraction will be. And ionic charge, the bigger the charge, the stronger the attraction will be. I'm going to use sodium and chlorine as an example. So the equation to represent the hydration of sodium ions is this one here. And the equation to represent the hydration of chloride ions is this one here. Now, the size of the charge can't really compare because one's a positive and one's negative, and also they both have a 1. So sodium has a charge of 1 plus, chloride ions have a charge of 1 minus. So the hydration enthalpies for this are going to be different because it's going to be down to the size of the ions. Now, and a sodium ion will have 2 electron shells because it loses its outermost electron to have 10 electrons. So sodium ion will have 2 electron shells, whereas a chloride ion will have 3 electron shells because it gains an electron to fill its outermost shell. Even though they're in the same period, the ions have different number of electron shells because sodium is going to lose an electron and chlorine is going to gain an electron. So for this, we would predict that because sodium is a smaller ion, it will therefore have a stronger attraction to the water molecules. And if it has a stronger attraction to the water molecules, that means the hydration is going to be more exothermic. And I have the actual hydration values here. So the hydration value for sodium is actually minus 406 kilojoules per mole, and the hydration value for chloride ions is actually minus 378 kilojoules per mole, and proving our prediction to be correct. So sodium's hydration enthalpy is more exothermic than a chloride hydration enthalpy because it's a smaller ion. So we would assume that the attraction between the water molecules and the sodium ions is stronger than the attraction between the water molecules and the chloride ions. Now we've looked at the factors that affect lattice enthalpy and hydration enthalpies in detail, we can apply this to predicting the solubility of a compound. And in basic terms, if we think a compound is going to dissolve, then the attraction between the ions and the water molecules must be greater than or equal to the attraction between the ions in the compound. In other words, the hydration enthalpies must be greater than the lattice enthalpy of the compound, because remembering that the attraction between the ions and the water molecules is to do with hydration enthalpies, and the attraction between the ions in the compound is to do with the lattice enthalpy. So this diagram here represents sodium chloride dissolving in water, and we can see that the chloride ions are separated, so the compound is broken down, and we can see that they're forming attractions to the water molecules, because water is obviously polar. Now, in order for that to happen, in order for the compound to break down when it's dissolved in water, because it doesn't just do it on its own, something has to physically break those ionic bonds, and it's the water molecules that have that strength. If the attraction is strong enough, the water molecules are able to break down that compound, overcoming the ionic bonds, meaning that the hydration enthalpies are going to be greater than the lattice enthalpy, because it's the attraction between the water molecules and the ions that actually physically breaks the compound down. So in other words, if the sum of the hydration enthalpies is larger than the lattice enthalpy, then the compound should dissolve. So mathematically, the sum of the hydration enthalpies of the ions in the compound must be greater than or equal to the lattice enthalpy of the compound. And if that is the case, then we can predict, or we can make the assumption, that the ionic compound will dissolve in water. However, there are other factors to take into account, such as temperature and entropy. Now, we should all know that temperature, as you increase the temperature, it increases the solubility of compounds. And then we also have something called entropy that will also have effect on whether a compound will dissolve in water or not. Thanks for watching. For more chemistry tips and revision, hit subscribe, click on the like button and check out my Instagram page using the link below.